Push the button. Alright, so we're going to start back here with action-reaction. Basically, it states for every force there is an equal but opposite force. Basically, for every force in one direction, you get a opposite force in the other. So like on this rocket here, if the engine put 20 newtons down, then 20 newtons of force had to go back the other direction. Alright, let's go ahead and look real quick at how we graph speed. If y'all look over here, I've always told y'all on any chart, circle your units. The reason for that is that tells you what this graph is measuring. If you look right here, this straight line says the person is covering the same amount of distance every unit of time. So a straight line on distance versus time is always a constant speed. If you look here at this straight line here, this says his distance is not changing. So this flat line says distance is not changing. That object is at rest. Let's go ahead and glance over here. Ignore this one up there. But if you look here, this one, the line basically curves down and goes to a flat line. That says you were going fast, but over time you slowed down and eventually came to a stop. So anytime it curves down, it is a negative acceleration, meaning it's like something slowing down. This is kind of like if you were driving a car and you slammed on the brakes, your speed would get smaller until you stopped. Or if you were running in the hall and then someone told you to stop, you would slow down until you came to a stop. This green one right here, this is a positive acceleration because the speed gets bigger towards the end. Basically, he's covering more distance. So anytime you see a curved line, think in acceleration. If it curves up, think positive. If it curves and flattens out, think negative. So this one is something speeding up. This is someone slowing down. Alright, let's go ahead and go over our forms of energy. Radiant is light, basically. Chemical is like stored energy, like in food, sugar, glucose, gasoline, any of those sort of things. Thermal is heat. Think of like thermals like you wear when it's cold. Electricity is basically electrical. It's going to be the flow of electrons going through metal. Then you have potential, which is basically going to be stored energy. And you have kinetic, which is based off of movement. Like, basically, if something is moving, it has energy. Alright, let's go ahead and look at some examples of how we convert these. If y'all look up here, think of potential as height. Think of kinetic as speed. If you look up here, this guy has the most potential because he's at the highest, but the smallest amount of speed because he would be moving the slowest once he gets to the top. Then as he moves down here, at B, he would have the most kinetic, but the smallest potential because his height would be the smallest. And then here at C, have about 50-50 of both because he would have some speed because he went up this hill, but he hasn't gone all the way back up to the original height. But he would still have some potential because he's up here at the top. Alright, let's go ahead and look at some basically energy transfers on how these work. Basically, according to the law of conservation of energy, you do not create or destroy energy. You only change it from one form to the next. This little awesome drawn sun represents sunlight. That's going to be called radiant energy, and it gets turned into chemical energy by our plants. They use their chloroplasts to turn radiant energy into sugar or glucose, which is chemical. Alright, this is a battery here. The battery in a flashlight is actually chemical because the acid has to react. Now if you put two pieces of metal there, it makes a complete circuit, and you have electrical energy, which flows through those wires to your light bulb, which produces light. Over here we have a like a water mill or like a hydroelectric dam. You have the kinetic energy here of the water moving. That's going to be movement. Whenever it pushes against this turbine, it's kind of like a fan, if you will. The water spins it, and as it spins, that is mechanical energy because it's turning. Think of this like a car wheel. If it turns, it's mechanical energy. And then that gets turned into electrical. Those are supposed to be power lines. But you use these sort of like a hydroelectric dam to convert electricity into, mechanical energy into electricity. Alright, if y'all look here, this is basically the review I emailed out to everyone's parents. If y'all look here, on number 1, now this is not going to be the one that you staple, this is going to be the one we did on Wednesday. You have 2 cars with different masses going down a hill. Basically the best answer is the car with the smaller mass, because it's lighter, has less inertia, will take less force to stop than the heavy car. Think of this like an 18-wheeler going down a hill. It's harder to stop because it has more mass and more inertia. Alright, let's go ahead and look here. This one is a very similar example. It has this cart going down a hill. The best answer, because it doesn't show you any force other than gravity pulling it down, is the car will increase its speed because it has unbalanced forces acting on it. If y'all remember, unbalanced forces will cause an acceleration. If y'all look here, we have basically a set of toys that were accelerating down a ramp. This is their masses. And they want to know which one had the greatest force. So you just use this equation here. Force equals mass times acceleration. You multiply across for each one. And you'll find out number 4 has the greatest force. Alright, let's go on to our next one down here. This is basically a boat. During the question it says that if it went from having 1 meter per second current up to 2, what would happen? And if you remember, opposite forces subtract, so the boat would get slower because more current pushing against it makes it go slower. On number 5, when the current changes pushing with the boat, it would cause it to basically speed up or move faster. Alright, if you remember, we already worked this out earlier in the video, but basically you rearrange your equation for acceleration, then you subtract your forces to get 66. Then you would divide by the mass of the cyclist, which is 100, giving you 0.66. Now, don't really look at these answer choices over here, because basically there was a typo. This decimal thing, the exponent here interfered with the formatting. So this is the best answer. It was basically have 66 meters per second forward, and that's based off of the law of force and acceleration. Now, if y'all look here, if the kiddo jumps off of the sled and there's no friction, according to action-reaction, if he put 40 newtons forward to jump off, there has to be 40 newtons going backwards, which would cause the sled to go east with 40 newtons. Think back to whenever we did the experiment with the rolly chair and me hopping onto a desk. Alright, let's transition over to the one you got on Thursday. If you look here, if the person pulls the cart away, there we go, that's a little bit better. Alright, if the person pulls the cart away really quickly, the inertia of the cart wants it to stay still until gravity pulls it down. So the best answer is going to be A, and it wanted to remain still or using inertia to stay in the same location until the unbalanced force of gravity pulls it down. Alright, if you look here, the key for answering number 2 is